that we can start. So good morning to everyone. And today we have the pleasure of having Renate Loll from Radboud University, that is currently a professor of theoretical physics at the Institute of Mathematics, Astrophysics and Particle Physics. And she's also a distinguished visiting research chair at the Perimeter Institute in Canada, Waterloo. So Renate in the past year works extensively in developing quantum theories of gravity and proposing innovative approaches to non-perturbative quantization of gravity. So today we have the pleasure to listen to her talk that will introduce to us and explain the main challenges and motivation that quantum gravity is presently facing. So Renate, the stage is yours, and thank you so much for being with us.
Yes, so yeah, I'm very pleased to meet you online. I'm reaching you from the Albert Einstein Institute in Potsdam, actually. So I'm on sabbatical and I have been traveling around and yeah, trying to get some work done. So today's question, so I did look at, you know, who the group is and what you're doing in terms of background. So my understanding is that there are no, experts in quantum gravity. So I'm keeping it on a level that has some basics in it, but also hopefully stuff that's interesting and hopefully, you know, relates to, well, in some ways to things maybe you are thinking about more from a classical point of view. Okay, so I've arranged this in the form of questions that give me an excuse to talk about various things in quantum gravity. As I said, starting with the basics. Okay, so to preview, so it's of course what I can do in 50 minutes is not more than a kind of broad brush account of the field. So I look very little into the past, but sketch kind of main approaches. Where have things come from and how are they developing and what is the future? And of course, I have a specific way of thinking about it, which I'll also introduce, which is, well, really, a quantum field theoretic way of trying to understand quantum gravity, but of course, beyond perturbation theory. So what can we do there? So you're getting a very, a cross-section and a selection of stuff I've written down in lecture notes, which I have already emphasized in the abstract. It's called the Quantum Gravity in 30 Questions, which I wrote up after teaching at a school on Corfu last autumn. Okay, so some health warnings are in order. As you are well aware, quantum gravity is not a settled theory yet, and that of course also means that people do disagree, where it should be going and what are the important points. The subject is very technical, but this talk won't be technical. Of course, I'll highlight where problems are, but of course, I cannot possibly cover technicalities in this shortness of time. And I cannot be comprehensive. So also I cannot give you the full story, which is, of course, people have studied quantum gravity, well, depending on how you interpret things, from the 1930s onwards. So that would be a lot of ground to cover. So there are different approaches, as I have already highlighted, kind of the way I'll be going roughly. So I'll try and stay, however, clear of ideology, although, of course, I'm presenting a point of view, and I have worked in the field for many decades. So, it's just a window onto the story. So the main message I want you to take away is that there is we are definitely progressing beyond, making internal progress within approaches. And the field is, to my mind, moving in a promising direction. Will we be able to finally connect to phenomenology? Well, we very much hope so. But no promises. All right, let's get just a little warm up. So what is quantum gravity? Let me just define what I'll be talking about. So it's the attempt to find a fundamental quantum theory underlying Einstein's theory of general relativity. So primarily, what we want to understand and also quantitatively describe is the structure and dynamics of space-time on all scales, because gravity, following Einstein, being encoded into the structure of space-time, the curvature structure of space-time. So that includes, of course, the very small, where we believe, quantum effects will be important, and we want to describe quantitatively how gravity behaves and how gravity behaves in its interaction with matter. So here, this little hand drawing. This just covers, I mean, you know, the range of scales that theoreticians are interested in. So our playing field, and of course it has to be logarithmic, starting here, the realm of quantum gravity. So 10 to the minus 35 meters, that's the famous Planck scale, right, which you get when you put together G Newton H bar and the speed of light to get a quantity of the dimension of a length. Here you see, well, this is us, length scale of 1 meter. So where the interesting question is, what role does gravity play? Well, basically the realm of Einstein's theory is really large scales. So classical gravity. I mean, you know, we can test, I think, the Coulom's principle, I forget now, is it millimeter and nanometer scale to some extent? So that's a part of Einstein's theory, but really we know the theory very well on large scales. And of course, putting symmetry assumptions, standard cosmology is also based on Einstein's theory. So that, of course, seems to give a reasonable description up to the very largest length scale of the visible universe, so 10 to the 24 meters. So what happens then on smaller scales? Well, there seems to be a whole range of scales where gravity, say, when we now start talking about, you know, going to small scales, going to atomic and subatomic scales, gravity is just so much weaker than the other three fundamental interactions that it doesn't seem to be playing any role. So it seems, you know, when we do scattering experiments, we can ignore gravity. But then also we think, so the reasoning goes, once we get to this very tiny scale here of the Planck scale, then really quantum fluctuations of the gravitational field or whatever is there should become large, and we have to take them into account. And well, of course, what we are hoping, you know, people who practice quantum gravity, is not just that all quantum effects will be just confined to that scale, but we hope that there is a phenomenology that somehow has left by whatever mechanism or is leaving its footprint on larger scales where we can connect them, you know, with macroscopic observable signatures. So that's the hope we have. And that's where we ultimately want to get to in quantum gravity. Okay, so what direct phenomena are we interested in describing? Well, there's, you know, the one reason that's very often given, and I think it's a good reason, is to say, well, the classical theory is just incomplete. I mean, it has a limited range of applicability, and if you go to very small distances or very, very large energies, then we're getting close to singularities that generically occur in the classical equations. So like those at the center of a black hole or at the beginning of the universe. Yeah, so what we see there is, well, there are unphysical infinities, and if only we had a theory of quantum gravity, we might be able, you know, to go that little bit closer toward, you know, the very origins of our universe and have a quantitative description there. Was it would be all the way to whatever we want to call a beginning? Well, we don't know to what extent our methods can describe that. So anyway, so we want to describe now, as I said before, I mean, gravity and space-time on very short scales. And then people have for long speculated that something very, you know, violent might happen with space-time if it starts quantum fluctuating. So, you know, people draw pictures of kind of bubbly space-time foams, and of course that's a notion that's been coined long ago. And it's just the expectation that if we go to very small scales, well, certainly space-time will not look as it does classically. So like a nice, smooth kind of entity where when we zoom in classically, things only get flatter. So from a quantum physics point of view, we expect exactly the opposite, that the more we zoom in to tinier and tinier scales, eventually we would start seeing quantum fluctuations. Yeah, and these would be maybe extremely violent, and maybe, well, space-time might look, you know, as wild as is depicted here. That comes from a two-dimensional toy model quantum, non-perturbative quantum gravity. So not at all nice and smooth, or it could be even torn apart and develop whatever, different topologies, wormholes. I mean, people have speculated endlessly, and very, let's say, popular speculation is that space-time itself may become discrete at a certain short distance, a Planck scale or below the Planck scale. Okay, so we want to describe these. So this is, of course, all just hand waving what I've been saying, but we want to find a quantitative description of these phenomena that uses quantum theory. So in terms of possible applications, I have already mentioned, it's kind of the very early universe. So more concretely, what might one dream of being able to do? Well, we always, when we're starting to describe the early universe, we are assuming, oh, there's some de Sitter-like background on which there live some quantum, fluctuations, which then, get expanded during inflation. Well, you could ask, you come up with the model that produces maybe more elementary, can say something about the quantum origins, the deeper quantum origin of any fluctuations that may live on such a background. And then, of course, getting back to the one big question, are there observable quantum gravity imprints that we can derive from a sufficiently complete quantum gravity, at, for instance, maybe within the reach of the next generation of gravitators? Now, why do we not have a generally accepted quantum gravity theory yet? So that's, of course, a whole long story in itself, but let me cut it very short for the purposes of this talk. So what is the one big difference with the other quantum field theories, fundamental interactions? Well, they're described as quantum field theories with kind of standard technology as described, in zillions of textbooks on flat Minkowski space. So that means, of course, we have a fixed metric, a fixed background metric, eta mu, the Minkowski metric. But by contrast, in gravity, that spacetime itself becomes dynamical, and it's no longer just a fixed metric, but a Lorentzian metric, which is, g mu of x in standard notation, which is the dynamical quantity. So we have to solve equations classically in order to understand what spacetime is, what its curvature structure is. I have already said, well, one reason why we don't yet have a theory of quantum gravity, and is because the scale involved, this Planck length, is just terribly small. And so in any experiments, it's difficult to come up with any suggestions, that would see these tiny effects. And there's, of course, also related to this, there are no experiments, unfortunately, to guide us in the theory finding, and there is currently no phenomenology to speak of, although people have thought in heuristic ways for a long time, systematically about what kind of astrophysical phenomena in more recent times, gravitational wave phenomena, might give us a hint of what lies beyond Einstein's theory, and therefore, maybe may relate to the quantum theory that underlies Einstein's theory. Now, the very old result is, of course, I'm just quoting these old papers from the 70s and 80s, is that unfortunately the standard way of setting up a quantum field theoretic quantization, namely perturbatively, in this case around Minkowski background, where we split the metric g mu nu into the kind of a fixed eta mu nu, Minkowski background plus small perturbation, and then treat these in linear perturbation theory, unfortunately doesn't work in the sense that the theory is perturbatively non-renormalizable. So one can try to quantize it, but then one needs to add kind of infinitely many counter terms during renormalization in order to cancel infinities, and therefore one ends up with a non-predictive theory. So for a long time, of course, this result has been staring us in the face, and it's been clear that it seems, therefore, that one has to go beyond perturbation theory. But then there is no canonical. This is, of course, what has caused also proliferation of approaches people have tried. So lastly, just a side remark, I expand more on this in my lecture notes, because some people say, oh, maybe gravity should remain unquantized. It is, let's leave it classical. I would say it's a very, from everything we know from 20th century physics, it's highly unlikely that this is a common way of thinking about it. For one thing, because gravity universally, of course, couples to all matter, and therefore matter is, of course, describes is a quantum phenomena, the dynamics of matter, and so therefore it would be very surprising if, in some sense, of course, that needs to be specified, gravity would stay classical. But let me not on this tangent anymore, but rather go towards the quantum theory. So but often in typical popular science articles about quantum gravity, the first sentence is, well, gravity deals with large-scale phenomena. Quantum theory deals with, tiny atomic, subatomic phenomena. And it seems that those two are incompatible. Okay. So, well, it always makes me slightly itchy, this type of statement, because, well, why should they be? I mean, we are exactly looking for a way to combine fundamental principles from quantum theory with fundamental principles of geometry, describing gravity coming from Einstein's theory. So it's a bit like, comparing apples and pears. So the point of view I would take is to say, okay, we have something that's quantum field theory, is a standard framework, but now we have to, well, our challenge, or one way of phrasing the challenge, is we have to adapt standard quantum field theory to the case where the spacetime is not a fixed background, but is dynamical, and is dynamical that allows me to describe large quantum fluctuations. I mean, beyond linear perturbation theory. So that means, of course, the background, some people then often call that a background independent way, quantum gravity. And I would say it's merely the analog of what is just a familiar feature from classical gravity, where I said before, I mean, we don't start with putting in a background typically, but we just solve them, maybe subject to some simplifying symmetry assumptions. So in the same way, you would expect that in the quantum theory, well, you can write down some quantum dynamical laws, and you have to solve them in order to understand what you mean by quantum gravity, by quantum space-time. Now, one of the reasons, of course, why this has been complicated is the fact has to do with the starting point, with the classical starting point that we have, and that we put in when we start thinking about quantum gravity usually. So how do we describe curved spacetimes classically? Well, we open our textbooks, and there is just, as you're all very familiar with, there's a beautiful description in terms of using the language of differentiable manifolds. So curved spaces a priori, of course, don't allow you to do any calculations, but in what comes in the package of differentiable manifolds is that we can use charts, right? So I have some curved manifold, with some metric G mu nu, then I always can cover it by, a set of local charts, where in the charts I can just use coordinates as I would do in a linear space. So just like writing an Rn, of course, I mean R4 in the physical case. And the beautiful thing is, of course, having these charts allows us to, write down and solve differential equations, just as we would do on flat space. But now in the presence of curvature that we encode in a expression that depends on G and up to second derivatives of G. And that's this, of course, the famous Riemann tensor. Now, this is beautiful and powerful, but it comes with a huge redundancy, namely what classically we think of as a freedom to choose any charts. Yeah? And it doesn't bother us too much classically. On the contrary, it can be, you would, for a given problem, you would typically look for adapted coordinates that make your problem, look as simple as possible. But this freedom, this classical freedom, just becomes a very annoying feature once you get to the quantum theory, because it's a redundancy in the description. And the point is, for example, when you do a path integral, what we have to do is we should be taking a superposition of physically distinct configurations. So when we do that, of course, we shouldn't work with the G mu nus because they have this large coordinate redundancy, or in other words, four-dimensional diffeomorphism, which still acts on these G mu nus in such a way to not affect the physics. So we have here the point that the standard coordinates we are writing down in this framework, and it doesn't really matter that it's G mu nus, I could be working in a first order formulation. Not all degrees of freedom that appear in G mu nu are physical degrees of freedom. So we have kind of gauge degrees of freedom in there as well as observable ones. And well, of course, it leads to well-known problems that now, with, of course, knowing very well about problems appearing in gauge field theories, well, we are quite used to, but nevertheless, they're already at the start of the development of general relativity led to many misunderstandings. So I'm just mentioning few, just confusing what is, or not knowing how to distinguish between what is a coordinate effect and what is real physics. So, as you know, so the status of the event horizon of a Schwarzschild black hole was a source of great confusion to people, as was even to Einstein, whether or not gravitational waves are a genuine physical phenomenon or also just a coordinate effect. So it's very interesting just to look into the history. So what I want to say and highlight is the problem of having to distinguish between physics and gauge leads to really serious problems once you get to the quantum theory. So I would claim that they are significantly worse than the classical one in the classical theory. Now, what choices, how do we distinguish different approaches to quantum gravity? Well, one has to make choices, when one goes beyond perturbation theory. And it's helpful to look at different choices that people make and makes them explicit, because then it will help us understanding, why formulations can look very different. So to start with, we have to make a choice of what the microscopic elementary degrees of freedom are. So think of them as whatever fundamental field degrees of freedom, or more exotic things, some kind of building blocks. So these might describe, conservatively speaking, geometry. Something like G mu nu, or something, pre-geometric. So some people, or many people, I should say, like to play around with certain discrete structures from which they imagine, continuous metric spaces will emerge. One could also think of making topology dynamical, making dimensionality maybe dynamical, or at least considering possibly more or perhaps even fewer than 4 dimensions to start with, and then kind of hoping that dynamically things will end up in the right dimension. And of course, besides just local fields, we might and have, of course, considered extensively extended fundamental objects like loops or strings of rates. So that's the first choice one has to make. So then it comes to kind of fundamental principles that govern whatever dynamics you're describing. So I'm thinking here about things like locality, causality, unitarity, which of course causality and unitarity need already some way of being able to talk about space versus time. So some people like to work with, say, Euclidean, quantum gravity, where there is no time. So then that would be, a choice where some of these fundamental principles are simply not present in the Planckian description. Then you might say, or prefer grand unified, or believe that only that grand unified theories where you include all matter should be considered or not. I mean, I would say the jury is out on that. Many people are fond of fundamentally discrete formulations for quantum gravity on very short scales. So these are the fundamental principles, and somewhat related are fundamental symmetries that you might want to, postulate should remain important when we get to Planckian scales. So diffeomorphism symmetry is, of course, just the most conservative choice, just being already there in the classical theory. Gauge symmetries, could appear depending on how you extend your microscopic degrees of freedom. Supersymmetry may make an appearance. Things like duality may appear if you're and has of course appeared in the form of ADS-CFT and made inroads into gravity. And very lastly, we need a dynamical principle. So that's the quantum equation, the quantum analog of the Einstein equation. So I put this in inverted commas. I mean, it could be various things, but they are just, roughly we distinguish between covariant or path integral approaches and canonical quantization, where we work with a 3+1 split classically and kind of advance, and then, various things have to be satisfied in the quantum theory. So even though such things in simple examples are, of course, equivalent ways of thinking about the same theory, the fact that quantum gravity isn't known yet means that often these different approaches can just look very, very differently in what they're trying to do and the ingredients they're working with. So here, that's a question I like, that's being leveled at people who say it's something meaningful to think about physics at the Planck scale. People say, well, look, we cannot perform any experiments there, so aren't you simply just free? You can just play around with whatever models you postulate or dream up at the Planck scale, and one is as good as any other. Well, fortunately, it's not quite like this. So even at to zeroth order, it's not true that anything goes, and that's even before we have developed, say, any true quantum gravity phenomenology. So, one thing one does have to show, of course, if one has, written down in quantitative terms some Planckian quantum gravity theory, is that when one kind of zooms out or one goes to larger scales, there must be something like a classical limit where you do recover at least some features of general relativity, which we know to be a perfectly good description on sufficiently large scales. Okay. Now, so this is actually a very non-trivial requirement, especially if you just start from a totally crazy, some totally crazy formulation at the Planck scale. The problem in practice is very often that such Planckian formulations are not sufficiently developed to be able to say what one means by the classical limit. And that's often highlighted as a crucial difficulty in non-perturbative approaches, and to some extent that is correct. Now, especially but people who maybe don't work on quantum gravity full time, or have studied various the problems of the non-perturbative theory, that tend to be made, I'm writing overblown expectations, so maybe overly optimistic would be a better word, overly optimistic expectations to what extent one can recover, structures that are simply present macroscopically and described by Einstein's GR from a starting point, that's just kind of quantum bits that interact in some ways, on very short scales. So it turns out, so why am I saying, it's over optimistic? Well, there is a large body of research where people have looked at statistical models of what I would call random geometry. So this is really, kind of quantum bits, of whatever, according to very simple kind of GR-inspired dynamical rules. Now, these have been studied in the form of toy models in lower dimensions, especially in the 80s, and were then really motivated by people who wanted to understand the non-perturbative dynamics of two-dimensional string world sheets. So that was when people were looking at boson to do it, going beyond perturbation theory. And then you end up very quickly with, you're looking for a theory that allows you kind of arbitrarily curved two-dimensional surfaces, that might be embedded in a higher dimensional space. So people started studying these objects by, building up these surfaces from, let's say, triangles, some fundamental building blocks, and then, and letting them interact. And so you do get, say, in lower dimensional Thomas, again, some, beautiful structures that are illustrated here by this picture, created by actually a colleague of mine, Timothy Butt at Radboud. But what turns out, when one tries to apply the same building principles, as I said, they're quite simple-minded, but kind of straightforward in higher dimensions, it seems that things go really badly wrong. So if you want to, formulate quantum gravitational path integrals beyond 2 dimensions, one has discovered, just by doing the explicit studies, often with the help of computers, that these systems don't generate extended spacetimes, but they run into very generic kind of what I call entropic effects, that, if you like, are due to the path integral measure. Sorry to throw a bit of jargon at you, but what typically happens is, for instance, that these geometries that you build up and that look, microscopically maybe 4-dimensional because you're using 4-dimensional building blocks, when you zoom out, don't generate a nice extended, say, 4-dimensional spacetime, but systems that, for instance, may look like branch polymers, so something that is essentially 1-dimensional. And it turns out this is just very generic. So if you have, you dream up, you have some intuition of what a Planckian quantum gravity theory should look like, have a look at what the classical limit is and study your model explicitly, and most likely you will find it described, if you're lucky, you'll find it describes branch polymers or some other, highly degenerate objects, but nothing that has GR as its classical limit. So that's something we have learned from studying these systems. When I say we, of course, it's a collective we, but work I am doing is, to some extent, in the tradition of these approaches. Now, so here a little, let us step back a little, or let me step back a little and show you a little piece of history. I mean, how the field has developed. I mean, emphasis kind of how, say, after the discovery that perturbative quantum gravity doesn't really work, how have things developed from there? So we have here on the left kind of the covariant branch, where one focuses on G mu nu minimally plus possibly other fields. And then there is the canonical branch where one has a 3+1 decomposition and has spatial metrics and conjugate momenta. So basically extrinsic curvature as the basic variables. So in the covariant tradition, which is of course also more, the particle physicists' way of thinking about quantum gravity, there are lattice approaches for quantum gravity. I mean, kind of similar. People try to emulate the successes of something like lattice QCD. There's quantum logic calculus that has been practiced since the 80s. There is Euclidean quantum gravity that is, basically Euclidean path integral, mostly, studied or advocated since the 1970s by Hawking and collaborators. And of course, then there is a big development since the mid-80s of superstring theory, which has G mu and much more, of course. So what one wants to do here essentially is, implement one of these dynamical principles, and namely here it's a path integral. So I'm writing that down here very schematically as the famous sum or integral over histories or geometries. So G is just short for G mu nu, or an equivalence class of G mu nus under coordinate transformations, and this is e to the I SG, where S of G is, say, Einstein-Hilbert or some other gravitational action. Now, this should be contrasted with the canonical picture, where one performs the split and then looks non-perturbatively to find kind of suitable operators, analogs of these classical variables, and quantize the theory based then on some algebra that is either formed from G hat and pi hat, or some composite quantities. So canonical quantum gravity is something that people have been studying for a long time, starting with the likes of Dirac. But of course, it really lies quantum gravity with 1980s. One was zooming, first of all, one would use a slightly different first order start that allowed one to introduce kind of loop variables, kind of Wilson loop type variables in gravity, and build up the quantum theory. Now, here one has the dynamical problem presents itself differently. So the key question here, kind of, if you like, the quantum analog of Einstein's equation is basically given by the so-called Wheeler-DeWitt equation, where this H hat perp is the so-called Hamiltonian constraint of quantum gravity, and this applied on physical wave functions should give zero. And what you're looking for are, well, of course, a good implementation of what this operator is, and then you're looking for wave functions psi that solves this equation. And this is very hard, and this is also very hard. So there's, again, as one often has in physics, one chooses to overall conservation of nastiness, but there are also definitely common issues one can pinpoint. So number one, of course, because we're talking about field theories at the very least, things with local degrees of freedom, of course, one expects that one needs to regularize and renormalize them. And the difficulty then with the question I mentioned previously, the gauge versus physics, is to do that in a way that is compatible with diffeomorphism invariance, that doesn't mess with diffeomorphism invariance. And, well, what one also needs is, of course, suitable tools, theoretical and computational, to handle these problems beyond perturbation theory. So, and yeah, what should one be doing again? So let's zoom in on the tools. So what, look, what's at our disposal, and so what can we expect in a way a theory of quantum gravity to be and to do for us? So it's asking this question is to some extent setting expectations. Now, so what is quantum gravity? I would say at best, in the simplest of all cases, it's a strongly interacting quantum field theory with highly non-trivial field content and symmetry structures. That's already familiar to us from the classical theory. And, well, outside perturbation theory, unfortunately, with this such a type of quantum field theory, it's very difficult to compute anything analytically. So that's, of course, what we already know from just studying non-gravitational quantum field theories. So what are cases where we are able to say more analytically? Well, these are the examples, the known examples are low-dimensional, two-dimensional field theories. Think of, the Ising model. Think of more general conformal field theories in 2 dimensions. Think of algebraic quantum field theory, right, where people try and put up QFT in an axiomatic way, but explicit examples that are in 2 dimensions. Think of integrable systems where often, large amounts of symmetry helps you, writing down conserved quantities and make progress in that way. Think of matrix models. Think of, more recently much studied tensor network models that come from quantum many-body physics, but also people have actually tried to apply to gravity. So the problem with all of those is that they are as solution techniques, beautiful in 2 dimensions and work, at least in sufficiently simple examples, but these do not generalize to higher dimensions. So typically we are stuck if we want to do things analytically, pen on paper. Now, what's an alternative? An alternative is, if we have what I call a magic wand. So, and the example here is, the ADS-CFT duality. So where you're saying, okay, there is a certain equivalence between, a strong coupling regime with one type of theory, in this case, gauge theory, on the boundary, and a different coupling regime, in this case, weakly coupled theory of gravity in the so-called bulk. So that's what the ADS-CFT duality is. So in the best of our cases, there might be, a difficult computation on one side that you might, by this, magic wand of the duality that exists, be able to attack, with other methods. So unfortunately, of course, so that's kind of the standard way in which the duality works. However, what we are interested in is, in a way, we are interested in short distance phenomena in gravity, very high energy, and it's unclear to what extent this duality can work there in the bulk. So I think that's, to my understanding, a largely unsolved issue. So what I want to do is do something, different, and rather look for methodology that allows me to address this non-perturbative Planckian regime directly. So try and understand, what's the physical content, try and understand the dynamics, try and understand whether I can make any predictions, and can verify things one, may on some theoretical grounds conjecture. So that will give us quantum gravity, reality checks. So what is essential here, because I explained to you on the previous slides that we do not have analytical methods at our disposal without, any other magic wands being around. Crucial will be numerical tools to understand what's going on. Namely, analytical methods currently do not. So what do we have at our disposal currently? There are essentially 2 things I want to highlight. One are Markov chain Monte Carlo simulations. So these are really analogous to what one does in non-perturbative lattice QCD, which is, of course, extremely powerful these days. And we would be very happy if in gravity, we had progressed as far as lattice QCD has progressed in quantitatively understanding, say, particle spectra, in QCD. So we are not there yet, but we can attempt to do something similar. So here, this is what I mentioned earlier. Lattice gravity and dynamical triangulations is a kind of refinement of earlier lattice methods one can use, and they use Monte Carlo simulations as a computational tool. So the other kind of toolbox that has been developed very much for the case of gravity in recent times are functional renormalization group methods, where one studies, flows of coupling constants, which also needs numerical tools for their solution. And the key word of an approach that is very much based on these methods and has been applied to gravity is that of asymptotic safety. Now, as a general comment, I would say the quantum gravity community and also the larger theoretical high energy physics community have been very reluctant to embrace numerical methods. Well, one could analyze where this comes from. I think certainly in the case of the quantum gravity community, well, from being exposed to the beauty of the classical theory. Although, as I think especially you as a group of people know, there, of course, in order to look at strong gravity phenomena, you have to use numerical tools. Now, in the quantum communities, this attitude that we should be able to solve the theory on the back of a stamp just with pen and paper, that attitude is changing slowly, and there is a realization that using numerical tools one may be able to get simple information about quantum gravity or a set of quantum gravity theories in general that you currently cannot get in any other way. So let me trace the more recent history of the subject. And so I've chosen here a cutoff here. These were my two previous branches, the covariant branch and the canonical branch. And I've chosen here, as a somewhat arbitrary timeline to say, okay, what was there before 2000 and what has been developing since the year 2000? So we have here in the covariant side, as a very dominant in the theory community approach, of course, superstring theory. And here on the right-hand side, of course, with dominant within, so-called other approaches, but of course, I don't know, a couple of orders of magnitude smaller in terms of people who worked on this, there's loop quantum gravity on the canonical side. Now, these have run into kind of serious issues, I would say, that were very clear by round about 2000. So in superstring theory is, I think, basically its uniqueness, even if that would give us, quantum gravity or part of a superstring theory, how unique, it doesn't appear very unique. So is it therefore predictive? Is it therefore useful? And also the question, going beyond perturbation theory is not well understood. Not too dissimilar problems on the loop quantum gravity side. Solving the Wheeler-DeWitt equation has been just very, very difficult. And there's also a uniqueness issue in various choices one has to make there. So I'm not going to dwell on those, but rather say what's been happening since. So let me start by the canonical side. So people have sidestepped, doing kind of full canonical quantum gravity, and many people from that community have started, studying a kind of a related covariant formulation that goes by the name of spin foams. Many other people have are still looking at reduced models, so quantum cosmology or black symmetry reduced models or black holes, and apply the methods of canonical quantum gravity there. But these are different systems. These are reduced systems. That's not full quantum gravity. So that's, however, what we what we are interested in. So what what has happened on the covariant side is, what's become of superstring theory, where it has morphed into other things. So people have zoomed in on the ADS-CFT duality, the associated, principle of holography as a new kind of ordering principle, fundamental principle, possibly of physics. And more recently, there has been a revival, interestingly, of the two-dimensional Euclidean path integral, and people getting very excited about certain these two-dimensional toy models. Now, the lattice gravity models are still alive, and there are new approaches have sprung up since 2000. So causal dynamical triangulations is one of them, and asymptotic safety I have already mentioned is another one. Now, what's crucial, and the reason why I've drawn a box around these is that these are all kind of non-quantum, essentially quantum field theoretic formulations. So the trend has been away from kind of exotic ingredients, extra symmetries, supersymmetries, extra dimension, extra this and that, extra fields, but to more basic stuff, good old quantum field theory. Besides, there are also other models which are not really quantum field theory, but are more non-standard, use discrete ingredients, say causal set gravity is one of them, using some kind of quantum information perhaps to understand black holes in the first place, using tensor models or the spin forms. So what's the bottom line of this? I would say now, basically coming from here, we are learning and have already learned quite a bit on how to accommodate dynamical geometry in a purely quantum field theoretic context. And that's what the rest of my talk will give you a glimpse of. Now, there are, of course, this is not straightforward at all. So this transition to dynamical geometry, and it raises conceptual issues. For example, in the absence of a background, what do you mean by a scale? Yeah, so think of standard, renormalization group discussions. One studies physics, how physics behaves as one changes scale. Well, if you're in a theory where kind of scale, of course, is part of the geometry, and I have to solve the quantum theory before I know what the quantum geometry is, it's clear that the standard schemes have to be somewhat rethought. And what's also clear is, and I hope is becoming more and more clear, is that really approaches that one follows here and that are amenable to numerical methods have really a huge advantage over those that remain purely formal. So, and what I, in the remainder of the time, will zoom in briefly on are these two approaches. Sorry, here, the causal dynamical correlation, the asymptotic safety. I'll just describe them very briefly, and I hope it has your interest. It will be just basically one slide each. So just, to give you a feel of what is it that people are looking at and are excited about. So let me start with asymptotic safety. That's a quantum field theoretic approach that's formulated in the continuum. So the main hypothesis is that quantum gravity is a so-called asymptotically safe theory. So what it means is that one postulates or one looks for a fixed point of the renormalization group flow in the ultraviolet, so at very high energies, which renders all physical quantities free from divergences. So kind of it is a solution to the perturbative non-renormalizability. One hopes instead for a non-perturbative renormalizability, and this asymptotic safety conjecture is just a way to make this concrete. So what are the flows? The flows are the flows as a function of scale of infinitely many so-called running coupling constants. So the coupling constants, they will typically include G Newton, they will include lambda, but they will also include, say, coupling constants associated with higher order curvature terms. So those span the theory space. And then one tries to understand, one formulates kind of flow equations, how these constants behave as a function when one changes the scale, momentum scale K. And here kind of things do become, although one uses really a continuum framework and one relies on G mu news, do become non-perturbative because these flow equations have to be solved numerically. This has been done. It's a big industry, and people find UV fixed points in truncated versions that, and the truncation means one studies finitely many running couplings and tries to pin down the flow, understand the flow there. In those, many or all truncations one has studied, one finds interestingly these UV fixed points. So that looks very promising. What is difficult to assess is the quality and the validity of these truncations. That is kind of an intrinsic difficulty in this approach. How do we assess whether the truncation is a good one? Another kind of open question is one relies very much that a continuum formulation that simply uses really these classical fields remains valid all the way down to the Planck scale. Is that really correct? That is correct. And maybe crucially, can we find independent evidence of asymptotic safety and the existence of these fixed points, which do not make these assumptions? And one way of doing it would be looking at lattice gravity. So what's lattice gravity in a nutshell? In a 1-minute characterization, it's really, what is the philosophy there? It's the same as in lattice gauge field theory. One describes space-time as a, in this case, due to fixed lattice. So the lattice acts as a regulator, and the vertices of the lattice are a small distance a apart. A is your UV cutoff, and in the end, you want to study your regularized formulation with the finite lattices in the limit as A is taken to 0. And then you study kind of the phase structure of these models. So you look how they behave as a function of the bare coupling constants you put in there. So this type of approach has been followed in gravity since the 1980s. So first, as I would say, in a kind of naive formulation, where one puts first order formulations of gravity, so with a vierbein and a connection, on a fixed lattice. So it's really imitating very much lattice gauge field theory. So this was studied, people in various versions, and simulations were made, and anything interesting was found. So one slightly speculative, but not too speculative explanation is that, unfortunately, putting up such a fixed lattice really messes with diffeomorphism invariance. So this invariance is very badly broken. It's just gone. When you start putting things on a discrete lattice like this, it's just gone. So probably that's where the special symmetry of gravity has hit you. So a naive implementation of putting gravity on the lattice doesn't work. But fortunately for us, there is a more geometric and much less naive lattice formulation, and that's based on this old idea of using kind of dynamical and triangulated lattices. That goes back to Reggie, 1961, where he was interested in formulating general relativity, solving the Einstein equations without ever introducing coordinates. So that's a famous paper, and if you have not read it, I recommend you to do it. Now, the beautiful thing is, it hasn't done classically very much for us, but it really solves the overcounting problem in the quantum theory, and that proves just very, very important when you come to a path integral formulation. So it's this classical strategy. So a smooth curved manifold is described by gluing together building blocks, which are called simplices. So in 4 dimensions, it would be little 4 simplices. So there are pieces cut out of a flat Minkowski space. Yeah. So here is an example. The point is the flat geometry inside is completely specified when you specify the edge lengths, and the edge lengths play the role of dynamical variables in Reggie's approach. So when you start then looking at manifolds or of space-times, you obtain them in a regularized way by gluing together these types of building blocks. So you get piecewise flat approximations of 4-dimensional curved space-times. Yeah. And of course, in the end, again, you want to shrink these building blocks away because they are just a regulator. So the beauty of it is, of this prescription, that we don't have a coordinate-dependent metric G mu nu, because there are no coordinates, but all the metric structure is completely determined by giving all the edge lengths and giving the gluing data. So how are these triangular building blocks glued to each other? No coordinates are needed. And as I said, the full power of this idea is only unleashed in the quantum theory. Important if you formulate the non-perturbative Lorentzian path integral. Yeah, that can be expressed in terms of these triangulated lattice data. So the particular approach that I want to highlight, because also that's what I've worked on, is what's called causal dynamic triangulations, where you have building blocks that have just work with 2 types of edge lengths, one space-like and one time-like, and one can describe kind of space-times that we are superposing in a gravitational path integral, one just builds them up from these building blocks. And there are no coordinates, and indeed it's free of coordinate redundancies. So in a nutshell, what does this approach do? Well, it's a path integral. So in this yellow box, here is again, I restate what I wrote down before. This is the formal continuum path integral, the sum over history, so-called, written down here with the I, so Lorentzian signature, where G is an element of Lorentzian matrix modular diffeomorphism. And here you have, again, gravitational action, let's say Einstein-Hilbert or something more general. Now, this is a terribly ill-defined object as long as you don't mathematically specify what all these ingredients are. So CDT, so this is a causal dynamical triangulations approach, specifies every single ingredient of what this left-hand side is meant to be. And so you get a regularized version where you substitute all the smooth geometries by triangulated spaces, and you take those that have a well-defined causal structure, you sum over those, and each of them, with a little kind of measure factor, you sum over all these things, all causal triangulations, and then you remove the regulator. So you send this tiny lattice spacing to 0, and then you look for interesting continuum physics. So this is a manifestly coordinate invariant way of constructing the path integral, and very importantly, one can use powerful Monte Carlo methods to evaluate what this thing is after one has Wick rotated this thing. Unlike what's true in the continuum, where there is no known Wick rotation for curved geometries, there is such a Wick rotation on these piecewise flat spacetimes. Now, to cut a very long story short, so this way of doing things and treating the non-perturbative gravitation path integral cures some very deep problems. An earlier and purely Euclidean way of doing the same thing, Euclidean quantum Euclidean path integral based on a precursor of the same method, it's called dynamic. This has seen no evidence of higher order phase transitions, which are a prerequisite of defining a continuum theory. So what's the key ingredient that you compared to these other Euclidean approaches? It's really the causal structure which we require to be implemented at the microscopic level at individual configurations to the path integral. And so it seems that unless you really put this in at the microscopic level, kind of causal structure, and the time doesn't emerge from structures that are non-perturbative and purely Euclidean. So I will not say more about this, but just say, what can we now do with this? So we have now a path integral. That means we have a computational dynamical framework. And what does it allow us to do? It allows us to evaluate geometric observables in the sense of expectation value in a regime that's very, very far away from a classical regime and very far away from a perturbative regime. Namely, where typical path integral configurations look quite wild. So, like this, morally speaking. So they're nowhere differentiable. And none of this is surprising. I mean, one can easily see why this has to be so, from looking at much simpler quantum models. So what you should think of as CDT, that it is really to gravity. What lattice QCD is to non-abelian gauge theory. So a tool that enables you to extract information beyond quantum theory, beyond the perturbative quantum theory. It has, I don't have time to say anything about it, apart from saying, as a highlight, it has produced strong evidence that of the emergence of a macroscopic four-dimensional extended spacetime, whose shape and average curvature are compatible with a classical de Sitter universe with line element familiar. This is in proper time, it's a line element of a Wick rotated, so Euclideanized de Sitter universe. So that's very, very interesting. But I should write in the sense of expectation values only, so not in any local sense. So that's the highlight of what this approach has produced. So something, a quantum, you can call a quantum spacetime, whose properties we can further study, because there are certain quantum observables that are well defined and that we can concretely evaluate in this non-perturbative regime. So this is my last slide, highlighting, kind of giving you a feel for what these quantum geometries are and what one can say about them. So I said, we can understand. So we are, the computer produces kind of a vacuum state. So this is like a non-perturbative, the mother of all vacua. So if you like, the ground state of this non-perturbative quantum gravity system. Now you have to ask it questions if you want to understand what it is. And these questions are observables, which you need, so diffeomorphism invariant quantities that you need to evaluate in the ensemble that have led to this, this non-perturbative ground state. And one of the observables we can study is the dimension of space-time. So you might be surprised that the dimension isn't observable, but it turns out as soon as we leave kind of the realm of the classical theory, there are notions of dimensionalities that capture quantum properties and that do not necessarily attain the classical value for if you evaluate them on a quantum space-time. And two examples are the spectral and the Hausdorff dimension. And how can they be anything but four when we evaluate them in the quantum theory? How can this happen? Well, it happens because, first of all, the geometries that contribute to the path integral are very, very non-classical. And on top of that, you're taking a very non-trivial limit. You're shrinking, the lattice away. You're getting these nova differentiable objects. And in a very high energy regime, these just behave very, very different from classical. And to understand kind of how this comes about, one should really look at the path integral, which in this non-perturbative regime, gets a contribution from the measure or the entropy and from the energy. So that's kind of the bare action I put into to start with. So the important part is that there is a contribution from the entropy of states, that is microscopic states of the quantum theory, namely how many do contribute at a given fixed value of the energy. And the region where we see interesting things happening is where these are kind of comparable in magnitude. And then you get interesting new quantum phenomena. And one of them is the famous spectral dimension that in dynamic relations we studied back in the early 2000s. We had a four-dimensional, quantum vacuum state we generated by the CDT method. And we then measured its spectral dimension by, looking at how a diffusion process happens in this quantum space-time. So it's the analog of having kind of an ink drop fall, into a bucket of water. The speed with which the ink drop fills out volume, grows, can be used to measure kind of an effective dimension of the space where the diffusion takes place. And what we found is that the spectral dimension we extracted from a diffusion process on this quantum ground state was somewhere near 2 at the Planck scale. So a completely inexplicable value classically. But when we zoomed out and went to larger scales, it asymptotes to 4. And this is kind of the one quantum signature we can point to of a quantity that has been now, quantitatively determined as an observable in, to start with CDT, but also in other approaches. And people consistently find something that's 2 or compatible with 2. So it's a quantum signature we can calculate, and that is something extraordinary for a theory of quantum gravity, because we could ever compute anything. And now we can. It's a start. So last slide. What's the future here? There's, of course, much more to say, and you may have additional questions to this. So what I think is a winning ticket is really pushing non-perturbative quantum field theoretic methods to deal with, better understand how to deal with, even better understand how to deal with dynamic geometry, and combine numerical experiments, I would call them, with analytical considerations. So like formulate, certain conjectures, how a system behaves, feeding that back into the numerics, and vice versa, from things, observables you study numerically, drawing conclusions about, some analytic properties your quantum gravity theory may have. So the computer simulations really play here the role of experiments and reality checks. And again, I cannot emphasize enough, give you information you currently cannot get in any other way. So the CDT approach, that's actually my field of research, but I only, mentioned this in passing. The beautiful result there is it's the first, example of the emergence of a quantum space-time where we have not put in any background. So it's really a first principles, a derivation in a full quantum field theoretic, full-fledged quantum gravitational formulation, and we can show that certain de Sitter properties are present in the sense of expectation values. So that's beautiful because we hope we might be able to connect this to something like early universe phenomenology. So so where is the field moving? Hopefully in a healthy direction where people do not no longer argue about the fundamental ingredients of their approaches, but they start comparing approaches and the ingredients and start computing things and comparing what they're getting. So this spectral dimension is kind of the first quantum signature that has played this role, but there are more and different observables. And of course, once we have identified those and our approaches are sufficiently complete to be able to kind of nail them down quantitatively, at least in certain regimes, then we can start comparing approaches. We can start looking for universal properties of what quantum gravity is, and we can make genuine progress that is independent of any particular formulation. So, as I already said, where I believe we are closest to phenomenology is perhaps in looking at the early universe. So here, of course, what one really has to bridge is a gap between these very non-local, background independent outcomes, that come from studying really Planckian physics. They're formulated in a very different language and using very non-local quantum observables, and they're not straightforward to compare to the standard formulation, for instance, we use when we talk about the early universe, it's de Sitter-like. Then we are employing really QFT, on a fixed background and studying fluctuations and how they behave, say, before and during inflation. Nevertheless, I think we are getting much closer. There is a clear way forward with this methodology, and there are many interesting things we're currently doing, and we really hope that, to inject more physics into the subject of quantum gravity. And this is the end of my talk, and I thank you. I hope I haven't exhausted you I haven't thrown too much information at you. So thanks so much.
Thank you so much, Renate, for the very interesting, instructive talk. And now we have some time for questions. So if you want to just raise your hand or unmute yourself. I see Pedro, I see Carlos. I think Pedro was first. Go, Pedro, please.
Okay, thank you, and thank you for the very interesting overview and talk. I apologize. I was only able to enter your talk. I think 10 minutes through, but I think I got some of the main points. So I was wondering about one of these last slides you were showing about the spectral dimension.
Right.
So this is the building blocks are 4 simplexes, right? So it doesn't this in a way, why the number 4? So this doesn't fix in a way the dimensionality of the final space-time?
Well, people always thought it did. So people always said, look, we use 4-dimensional building blocks, and how can the final result be anything but 4-dimensional? So it has only become clear when people ask the right question. So, people were playing around with the Euclidean version of this. They used 4-dimensional Euclidean building blocks. This was this dynamical triangulations approach. And kind of the precursor of this causal variant, you could say. People, they generated also like a quantum ground state, but it took a long while for them to understand that it doesn't have the right dimensionality. So indeed, in this non-trivial continuum, things can happen, and the dimensionality changes. So I understand the flavor of your question. Can I maybe by some other dimensional building blocks generate something that's 4-dimensional? We know from kind of 2- and 3-dimensional building blocks, they don't seem to generate 4-dimensional extended spacetimes. So, and we haven't looked beyond 4 because it's kind of becoming difficult.
Yeah. So in a way, I guess I think it's still very interesting that it works in a way that you can actually produce some concrete results. I think that was one of the points, right? But then one has to motivate why to consider these blocks with number 4. And well, I guess we have the motivation of 4-dimensional spacetime, but if the idea is to have something which is bottoms up, so to grow something from a fundamental from first principles, then I guess one needs to provide an explanation for why consider a simplex with a 4-simplex, right?
Well, I let me disagree with you. So the thing is, of course, I had one slide where I was talking about, which choices have to be made a priori before I even can start, with the theory. So it is clear that some things have to be fixed a priori, some structures, when to start, talking about Planckian spacetime. Now, we have no indication that, or rather, all indications we have is that unless also your microscopic building blocks are 4-dimensional, you get an extended universe coming out. So that's a finding. I'm not saying it had to be. Or another finding we said is, well, unless it seems we put a causal structure into it microscopically, it never seems to come out. So I think, you see, well, I understand your question, but you see, if you followed that, we would say, well, we have to take like a superposition of everything, every dimensionality of building block, every possible fields. We should be summing over everything and then should study the dynamics of these models. But this is totally unrealistic, because if you consider too many microscopic states, then your partition functions, they diverge so badly that you can never make sense of them.
I see. Well, it's still quite interesting, even starting with that assumption that you can have something that, even though locally you have a spectral dimension which is not 4, in the end you can obtain something
microscopically, then it's, as I said, it seems to be dimension.
So it's a spectral dimension. So the dimensions that don't have to be integer numbers, right?
No, exactly. So it's like, of course, these dimensions can also be, evaluated on, say, classical fractals. And it's long been known then that the outcome doesn't have to be an integer. So,
okay,
there is a blueprint. There is a blueprint to understand, that things I can build from, fundamental building blocks. They can have a dimensionality that is different. So the final result can have just also and a non-integer dimension, as seems to be the case. So it really shows you there is some, quantum structures there. It's not intuitive. You would not have guessed it from any perturbation theory, around a 4-dimensional manifold, that this could happen.
Yeah, thank you. I don't want to monopolize this, so I'm going to lower my.
I'm happy to answer more, Carlos.
Thank you.
Okay, so thank you. But well, I'm happy if Pedro continues. Anyway, so first, thank you for this very well organized and really well thought of talk. I understand. Well, I can only imagine how difficult it is to kind of discuss these issues that become very technical to a more general audience. Well, my question is about data. And my question is related, I believe there was one slide, I may be mistaken here, but where you were asking why we haven't developed quantum gravity yet. And there was a list of reasons. Mm-hmm. And one of them, I believe, was that, well, we don't have any data about the Planck scale, or if I understood correctly.
No obvious quantum gravity phenomenology. That's what I said.
Yeah, okay. But if we look at historically the development of quantum theory, and here I'm thinking about, the one that we learn in a university degree and also particle physics, without atomic spectra, without the photoelectric effect, without the black body curve. And then if we move to particle physics, without all the resonances, I mean, of course, we have guiding principles. We have gauge symmetry with the gauge group that we use and the model. So in a sense, the data was all showing the way. And my question is this, I mean, so this is an extremely difficult problem, and this is clear. But isn't it a problem ahead of our time while we don't have data? Won't we need some sort of data? So my question to you is, can we converge? I guess you believe you can, because this has been your kind of focus for so many years. But isn't that without data, there's a strong risk that we will never converge, because the answer might be surprising somehow, and the methods may be not yet even the right ones available and so on, and the data will guide us towards that. So what are your thoughts about this? And I know I'd like to know your thoughts.
Yeah. So my thoughts are as follows. So I think it's a special situation which we haven't really confronted so much with theories, because there was always a way to test them, and now, well, we don't know. So you could ask, let me rephrase the question. So what is the most fruitful way, I would say, of studying quantum gravity, which, when you're a theoretician, there seems to suggest so much, everything we know, let's phrase it like that, we know about the other fundamental interaction suggests that there should be something like a theory of quantum gravity. Okay, so what seems to be the most fruitful way of going about this? So the way I've converged is, and maybe the community is also converged. So the community in the last 30 years had made an excursion into super complicated. The structure is beauty, and let us add more and more structure. So to a limited extent, maybe loop quantum gravity is an example of that. Then you postulate extended objects, or string theory is a much better example of that, where also you postulate fundamental extended objects, but then for consistency you find you have to add dimension, you have to add supersymmetry, you have to add so many different fields, and you end up with a Pandora's box of richness, an embarrassment of riches. And there's no predictability, because zillions of parameters are floating around. So I would say lesson here is try and be minimalist, with as few ingredients as possible, to construct something that has non-trivial properties. And so essentially, as I emphasized in my talk, I believe the inroads of really developing computational non-perturbative proofs to understand what our theories predict is totally essential.
Mm-hmm.
So there is a gap, there is what we can reach with experiments, what we now can reach with gravitational wave detectors. And there are certain phenomena we look for, perturbative nature that says, can we pinpoint any deviations from GR at all? Right. So that's where we are kind of on the experimental side. And are we sensitive enough to pinpoint any such effects? On the theory side, I think there is a big gap, because our theories are too incomplete to even make a concrete suggestion of what might be a good observable. So I've come up, as I mentioned the spectral dimension. So I would say it's the first time in quantum gravity that we've computed a number. So now, you can read, Steve Carlip has written a review of all the approaches that have studied the spectral dimension, and he hypothesizes that, this number 2 is maybe something universal. So I would say it would be very interesting if one could make this hard. There are theoretical formulations that say space-time on very short scales has dimension 2 in some sense. yeah, so I think that's the starting point. The next point is to say, what does it imply for phenomenology? Is there any macroscopic phenomenology I can point to where this quantum behavior, this funny dimensionality, would trickle whatever up or down into observations? So, and people have, again, our quantum theory is not sufficiently developed to do one, calculation, because we don't really understand well how the matter couples to the geometry in this realm, in this Planckian realm. But people have started thinking about, there are heuristic papers now that, people have put out saying, okay, the luminosity, in my graduation wave would be affected maybe heuristically in a certain way by this different dimensionality. So, but I would totally agree with you. There's still this large gap, but I can see, well, what we should be doing on the theory side is really make things much more concrete and use to understand what our theories predict, even on Planckian scales. We need these, and the Monte Carlo, let's substitute for an experiment in that sense. So yeah, I'm a great supporter of making, quantum gravity kind of these non-predictive tools, even if they're not exact, but that's well, that everywhere in physics we have, we working with non-existent in a way. Yeah, I would say there's really some psychological problem in part of the community that this is not accepted, in high energy here as a valid way of proceeding and trying to understand what your theory says. So, yeah. So that's my take.